You've been introduced to everyone on this list. This is a supplemental section on the role of simulation in education. My name is Mark Thorin. I'm a systems engineer at Analog Devices, and among other things, I contribute to the education program, the university program. It's one of my favorite things to do. And much of what I do when I'm writing lab exercises and things like that is involves simulation. So let's get started. So this is a famous picture of an old-time analog guru, Bob Peace, who started out working for Philbrick Research on some of the very first commercial operational amplifiers, so analog pioneer. And he was famously skeptical of simulators. If a junior engineer ever came to him and said, I don't understand why my circuit doesn't work, the simulator said it would work, then that would induce a scene like this. So simulators have been around since the 1970s. So 1973 was when the first version of SPICE was released out of Berkeley. This photo was taken in 1996, and of course simulators had evolved considerably since then, and they continue to evolve. And then a comment here that even Bob Peace mellowed out in his later years. He understood that simulators had a place, and we're going to look at some of those use cases shortly. So we are going to be using a simulator called LTspice, and LTspice is it's a SPICE-compatible simulator released by Linear Technology Corporation a number of years ago, before Linear Tech was acquired by Analog Devices. I came along with, I started out working for Linear Tech, so I came along with that package there. And why Linear did LTspice is the fact that switching regulators are extremely difficult to simulate. They're nonlinear circuits, they are discrete time, so discrete switching events, and Mike Engelhardt put together or came up with a methodology for rapidly simulating switching regulators. And while he was doing that, he realized that in tandem, he was really writing in his mind, and he's probably right, the world's best SPICE simulator. And so, rather than charge money for that simulator, we give it away. And it's also open, so it's not limited to parts from Analog Devices. If you have a third-party model from one of our competitors, it won't hurt our feelings if you import it into LTspice. So it's just a free, high-quality, unlimited simulator that we give away. And this is a couple of quotes here from a presentation or an interview that Mike did with one of our distributors that's posted up on YouTube, where he was asked, what is the point of LTspice? And he conjectures that some people think that it's a sanity check. His comment was, no, if you need a sanity check, then go see a therapist. Is that how you verify your design? Well, see earlier slide. You don't verify a design with a simulator. That's what the workbench is for. So what is the point? Well, the point of simulation is so you understand your circuit better, to develop intuition. There's no way to understate the value of cultivating intuition about how your circuit works. So that's a mouthful, but it's worth reading out in its entirety, because like this next sentence here says, when a circuit board revision, like a fiberglass circuit board, costs thousands of dollars, and more importantly, when mask sets for silicon die cost millions of dollars, then intuition and understanding your circuit are absolutely essential. You absolutely need to know what are the variations I can expect, what happens when I'm at a certain corner of the process technology or something, or things like that. So building intuition about your circuit. So let's think about how we can apply or use simulation in an educational environment. So obviously it's important in industry, but it also has a place very early on in a student's academic career. And so here's a little Venn diagram showing some approaches to university labs. And I'm not a professor or a PhD, but I did teach mechanical and electrical engineering at labs at University of Maine, and I've regularly take our lab exercises that we develop at Analog Devices. I take these out and present them as workshops at universities. And so we can sort of look at this Venn diagram where, at one extreme we have textbook only. So, consider a postdoc professor that is sort of buried in books and maybe up in an ivory tower, or insert other stereotype here. So that's certainly one approach to learning electrical engineering. There is a place for lab only, learning how to use instruments, learning how to follow directions, and that might be something in a technician's education. Let's get a laser pointer here. And then if you merge a textbook with simulation only, if you can't afford lab equipment, then a simulator is infinitely better than nothing at all. It is at least a way of, it's at least a way of I don't even want to say pretending. It's a way of running idealized lab exercises without any test equipment. So certainly a place for that. But merging all three into an active experiential learning experience is really the best approach. And that is something I can back up with a smart PhD's work here. So, Bob has published a number of papers, written a number of books on this approach, this very hands-on approach to learning electronics. Okay, so let's apply that to some actual circuits here that a student might encounter early on in their academic careers. So this is probably the third op-amp circuit that a student will encounter. So you typically will study an inverting amplifier, a non-inverting amplifier, learn the basics of op-amps, and then you come across this circuit, a difference amplifier. And one of the figures of merit of a difference amplifier is common mode rejection ratio. So what you'd like this circuit to do is take the difference between A and B, regardless of where they live in common mode, or regardless of whether they're parked up here at plus 10 volts or minus 10 volts or whatever. You want an expression of that signal, V out, reflected about ground, so brought back down reference to ground. And the way you test the CMRR of a circuit like this is to short the inputs together, so zero signal, and beat up the common mode a little bit. So here we are driving the common mode up and down by a volt. And what you'd like to see at the output is nothing. What you do see at the output, even in simulation, is this sine wave. But when you look at the vertical scale here, plus and minus 20 billionths of a volt. So I purposely chose this model of a real amplifier, this LTC 1150, because it itself has excellent common mode rejection and an extremely high open loop gain. We're also testing it at a very slow frequency, so you would expect great common mode rejection. And if I plug this in and do the math, I see a CMRR of 153 dB. This is an awesome circuit. Except when you actually go to build it, you're faced with reality. So if a student has 5% or even 1% in this case resistors available, maybe one resistor is 1% at the top end of the tolerance band and another is 1% low, a couple other resistors somewhere in the middle. If I run this, if I build this circuit and test it on the bench, how come I'm only getting 46 dB instead of 150 dB? Well, one part in 100 is 40 dB, and here I've got 1% value resistors, so that sort of makes sense. And if I run the simulation, I get 46 dB, and sure enough, I should also see that on the bench. So if you take the student who's got a frustratingly low performance circuit, send them to the most expensive meter that you have in your university lab there to measure these resistors. So get a real measurement of what these values are, plug them into LTspice, and see if you can perfectly model this imperfection. So if you're seeing a wiggle of plus minus 5 millivolts on the bench, do we also see this in simulation? Now you're starting to build intuition about your circuit. It didn't work, you figured out why it didn't work, and now you can simulate it with this, theoretically perfect simulation of an imperfect circuit. Furthermore, not everyone's going to have, not all of the students' classmates are going to have the same resistor values. They're going to be all over the tolerance band and that sort of thing. So we can exercise pretty quickly and easily. This is not a complicated circuit to enter into LTspice. We can include nominal values and we can include a tolerance. And by stepping a bunch of simulations, we can run, in this case, we can run 100 simulations in a matter of seconds. And we can get some idea of the spread of the spread of performance that we can expect. So simple experiment, a circuit that a first or second year student can build, and we're already looking at statistical spread of performance. And this is about the same time that a student will be taking statistics. So this is a real example of why statistical analysis is important. Okay. And let's see, link out to an article talking about some worst case examples, lots of examples out there. Okay, another use of LTspice is to model circuits that you can't build in the real world because currents are too high, voltages are too high, etc. And so I like this example because if the first switching regulator that a student might build may actually use components with these values. So a 5-volt power supply and a 100 microhenry inductor. In fact, we have a 100 microhenry inductor in the analog devices parts kit that we put together. What happens if the student holds these components in their hands and connects them together? Well, what happens is in 100th of a second, so the snap of a finger in student time, my current ramps up to 500 amps. Well, not really. In real life, if I hook this up to a 5-volt USB wall wart or something like that, something's going to give. My voltage is going to collapse. I'll go into current limit, something like that. But LTspice lets you see what would happen if I didn't have those limitations. And, sure enough, in 100th of a second, my current ramps up to almost 500 amps. Then I can start adding in reality factors, like the fact that this inductor is going to have some DC resistance. And sure enough, I see that, well, now my resistance is limiting my current a little bit. Or I can put in the maximum current of this voltage source. In the case of a USB power supply, it's half an amp or 1 amp for a high current charger. And so I can model that in LTspice and say, hey, this is what happens in reality if I put in these limiting factors. But if I want to take those away and see what the circuit would do if it didn't have any limitations, LTspice is fantastic for that. Or a simulator is fantastic for that. So another use for a simulator is to simulate things that would take tens of thousands of dollars worth of test equipment to perform in real life. So a great example of that is transmission lines. So for understanding Smith charts and network analyzers and transmission lines, there is no substitute for sitting down at the bench in front of one of these beautiful machines with a few different lengths of cables, see what an open circuit looks like, a short circuit, different lengths of cables and all that. Unfortunately, this box is $50,000. And if we had a slower, maybe lower cost piece of test equipment, let's say that went up to 10 megahertz instead of 10 gigahertz, I could still do those experiments with a longer piece of cable, but that's also expensive and bulky. So a 300-meter cable is about a microsecond. Well, that's at the speed of light. It's probably more like 2 microseconds down a cable like this. This spool of cable costs $130 and it's huge. So how can we use LTspice and some other setups to do some transmission line experiments? And here's how. Don't start with an electrical transmission line. Start out with an acoustical transmission line, like a Pringles can. And so this is an experiment that we're putting together. And in fact, if this looks interesting, please bug me after the session, and that will that'll light a fire to push this exercise out the door. What we're doing here is we are driving one end of a Pringles can with a speaker, and we are measuring the sound pressure level qualitatively with a microphone at the same end of the speaker. In this case, the end of our can is closed, that's a point where air cannot flow and air pressure can build. So that's analogous to an open transmission line. So open circuit at the end, I can't have any current flow, but my voltage, my potential can be quite high across an open circuit. Okay, so LTspice I can happily plug in 670 microseconds, an impossibly long electrical transmission line. LTspice doesn't care. It'll model this just fine. I can also plug in this discrete model or a lumped parameter model of a transmission line. So I can, in this case, I'm stringing together, looks like 15 inductors and capacitors. So again, one of the first things a student encounters when studying transmission lines is this LC model of a transmission line. Easy to draw on paper, pretty difficult to build in real life. You actually need lots of inductors and lots of capacitors, and to scale them properly, you end up with a pretty big, bulky circuit with lots and lots of components. Components in LTspice are free. So if we run this model, let's see what happens, or let's see what we get out of this thing. So this is the result here. So if I look at that near end of the transmission line in LTspice, I see these nulls. I see places where I get peaks in the response, peaks and nulls, peaks and nulls. And if I look at Scopy and measure the response with the network analyzer, I get, not exactly the same picture, but pretty close. I at least can tease out these initial nulls. And I can assure you that this experiment is just as satisfying to hear as it is to see. So I have this in front of me here, and I've got Scopy network analyzer, and it sounds about like this. And you get the idea. So, so again, this is the same instrument. There's no extra hardware than the M2K and Scopy that you were using for the Wien bridge experiment. Also functions as a network analyzer. So here we've drawn an analogy between a Pringles can and an electrical transmission line. We've modeled it in LTspice. We've seen that, yes, the model holds at 670 microseconds. Now I can plug in 670 nanoseconds or 670 picoseconds and see what would happen in LTspice with a much shorter electrical transmission line. So again, the point is you can model situations that exceed the capability and your budget for test equipment. Okay, demonstrating interesting equations to arbitrary precision. So, one of the purposes of LTspice is to simulate switching regulators. We're actually not using any of that functionality in these simulations. This is a basic model of a perfect boost converter. So the way a boost converter works is I take an inductor with an input power supply and I short circuit the inductor to ground. So this is that exact same circuit we looked at a few slides ago. So I've got a 5-volt power supply across a 100 microsecond inductor, but I switch it rapidly. I don't leave it connected. So I let the current build up to a certain value, and then I shut this switch off and I dump the energy stored into the inductor into an output capacitor here. And if I go through the math and I go through the textbook, every power electronics textbook derives this equation, where V out is equal to my input voltage over 1 minus the duty cycle. So if my duty cycle is 50%, then the denominator becomes, let's see, 1 minus 50, then I multiply by 2. If my duty cycle is 99%, I get a factor of 100 boost, and so on. So let's see what this looks like in LTspice. So LTspice lets us do things like this, and let's run this and see what happens. And let's probe our output node. So I've got 5 volts in, I've got a duty cycle of 50%, and I've got an output voltage of 10 volts. How close to 10 volts? So if I stop the simulation, the answer is really, really close. So here's 10.000 volts. Let's run another experiment. So let's take this. Oops. That is the wrong parameter here. Duty cycle. So let's go up to 90%. Oops. Okay. And so now we should get a boost factor of 10-ish, 10 or 11. Okay, how close to 10 or 11, we'll find out pretty quick here. Okay, pretty darn close. So it should be a factor of 10, and we're at 48 volts here. And actually, we do have some parasitics in here, and we also have a load. So let's increase our load resistor a little bit to 100 ohms, or let's make it 200 ohms. So I'm unloading the circuit a little bit. And you notice that I ring a little bit more. I've got less damping going on. But once that settles out, how close to ideal behavior do we get? And the answer is pretty close. So we're within, 0.3 volts or so of 50 volts. So again, this is a circuit that is impossible to build in real life. I can't get perfect switches. My inductor has no parasitic resistance. But again, what I've done is I've built a circuit that demonstrates the ideal behavior of that equation. Okay, so once we've got a circuit once we understand how the equation works, then we can move on and start adding in imperfections. So I can take that circuit and add in a real MOSFET and add in a real diode drop. And I can simulate this in LTspice and see what does this circuit do with real components. And I can run that simulation and see what its behavior is in LTspice. And then finally, I can build that circuit. So this is actually a model of an educational power supply circuit that that's actually released now. And what we see is that in real life, when I take measurements with the AD ALM2000 and Scopy, I get very, very close match to LTspice here. And in fact, this is just sort of a photo of a random simulation or a random situation here. It turns out the voltages, the output voltages that you measure in these cases are very, very close, within a few percent of one another. So again, this is about building intuition, understanding your circuits. If I can look at an imperfect circuit and understand the parasitics, understand why it's not perfect, then that is incredibly valuable. So let's apply some simulation. Let's apply this approach to Dr. Bowman's Wien Bridge lab. So he actually showed you this measurement with I think he did, show you this measurement using the AD ALM2000. So we take this Wien Bridge, and what did we learn about the Wien Bridge? We learned that whatever voltage that at resonance, at my oscillation frequency, whatever voltage shows up here is divided by 3 and phase shifted by 2 pi radians. And so if I'm divided by 3 here, I can build myself a perfect 3-to-1 divider on the other side of this bridge here. And also in LTspice, I can take a voltage-controlled voltage source and use this as the world's most perfect oscilloscope probe. So here I'm measuring the difference between C and D and looking at the output. And sure enough, what I see here is at resonance, 1.5 something or other kilohertz or so, I get this very, very sharp null in the output of the bridge here. So a 0 voltage at the output of the bridge. I'm also plotting VC, so the voltage at the output of the bridge, or sorry, at the output of the reactive leg of the bridge is this sort of gentle slope here. But again, if I look at the difference between these voltages, I get a very sharp null. I can pretty much perfectly model this circuit. We also learned a little bit about Barkhausen's criterion. Exactly. So, or I should say, let's model Barkhausen's criterion exactly in LTspice. And I can do that by taking the output of the bridge, and which I know has a gain of exactly 1/3 at resonance. And it's exact because, again, I've got perfect values here. If I apply that, if I bump the gain of my voltage-controlled voltage source from unity in this slide to a gain of 3, or, let's not be so ambitious right away. Let's start with a gain of 1% less than 3. And again, like in a real oscillator, if there's nothing to get it started, then it will just sit there and do nothing. So this V1 gives the circuit a little kick. And then after about 6 milliseconds, the output goes to ground and it's effectively out of the circuit. And if I kick this little circuit, I get some buzzing, I get some oscillation. But as expected, I'm not exactly meeting Barkhausen's criterion. I'm 1% away and my oscillations die out. So if we bump that gain up a little bit to, let's say, 0.1%, within 0.1% of where it needs to be, my oscillations persist for longer and longer, but they still die out. And if I bump the gain up to exactly 3, I get exactly a perfect oscillator. Once I set this oscillator going, it will persist forever, or until numerical precision of my computer gives up the ghost somehow. So again, I'm exactly modeling the textbook equations for a Wien bridge oscillator. And then the next question might be in your mind, if we went from a percent too low to 0.1% too low to exact, what happens if I go a percent too high? And the answer is, I very rapidly exceed the capabilities of anything you could produce in reality. So after a quarter of a second, my amplitude reaches 800 teravolts, and the internet consensus is that a bolt of lightning is approximately 10 megavolts to 120 megavolts. So again, LTspice or a simulator lets me break the rules of physics and see what would happen if my gain was a little bit too high. So let's take a little trip back to reality and run some simulations of Dr. Bowman's circuit here, and we'll flip over to LTspice in a minute. So again, we can model we can then go back. We understand how the circuit works. Let's do some experiments with the actual circuit in LTspice, and let's go back over to. Let's open up some simulations here. Wien bridge complete. Oops, cancel updates, and here we are. Okay, so now we're looking at LTspice. And so here's Dr. Bowman's oscillator, and let's take a look at some interesting things that we can analyze using LTspice. So as expected, we see an oscillator. It does what we expect, and we should actually get pretty close agreement to measured results here, right down to some of these little departures from an ideal sine wave. So there's nothing going on here that's terribly dependent on parasitics. I expect the model of my Oppo7 to be reasonably well behaved. The clamping behavior of these diodes is also pretty accurate. You'll notice that we have a little circuit here. We also have a little kick circuit here, because you can build this circuit 100 times on the workbench and it'll start up every time. But if you look at what happens at the very beginning, you'll actually see quite different behavior from circuit to circuit on this initial startup. And the reason is an oscillator, every oscillator or most oscillators in real life depend on some non-ideality to get started, noise or offset in an amplifier. You can always count on an amplifier having offset. It will always have noise. You just don't know how much. So let's take this little kick circuit. Actually, let's probe it to see what it does. Oops, zoom to fit. Yeah, so if we look at what this does, I start out with a minus 0.1 volt offset, or I'm sorry, with a 0.1 volt offset, and then I ramp down to ground. So after 6 milliseconds, this is out of the circuit. If I set V kick to 0, so again, effectively taking it out of the circuit entirely, how long does the circuit take to start up? 7 or 8 milliseconds? Now let's run it. Oops, can't resolve. Let's cancel this. What happens? Let's see, V kick, I want it to be 0. Hey, much better. Wow, look at that. So when I take V kick out of the equation, this circuit in simulation takes 150 milliseconds to start up. In real life, most circuits would probably start up quicker than this, but you never know. You might get lucky or unlucky depending on how you look at it and get an op07 with exceptionally low offset. If this startup time is important to you, if you're turning your oscillator on and off and it has to be up and running within 50 milliseconds, you better make sure that it's up and running by 50 milliseconds. And we can do that with a little kick circuit here. And this behavior, so if I bring that back up to 0.1 volts, the behavior of this circuit you would expect to be modeled accurately. Okay, and we are almost done here. So let's look at one other thing real quick. In simulation, I am going to start saving data a little bit later. So at, let's say, 0.1 seconds. That is a way of getting rid of, the simulator will still run the first 100 milliseconds of the simulation, but it will only display after that. And the reason we might want to do that is if we're doing a Fourier transform, so an analysis of this thing. So let's add, let's see, where do we go? Come up here, view FFT. So like we did in the real experiment, let's look at the distortion of this circuit. And that is all. We need to add some windowing functions here out of the scope of this discussion here. But this is a plot not unlike what we would see in Scopy. So under these conditions, let's look at our first three harmonics. And if we look at that cursor down at the very low part of the screen here, that's about 27 dB to the first harmonic or the second harmonic, and 57 dB to the next harmonic here. Okay, and then let's go in and make some changes to the circuit. Let's bring this down to about 4K. Let's bring it down to 3K. So if I bring that down to 3K and run the circuit, doesn't start up. My gain is 2, I don't meet Barkhausen's criterion. If I bring this up to 10K, okay, so I'm relying more on the clamping action of these diodes to limit my gain. Okay, wow, that looks kind of ugly here. So you can actually see some variation in the amplitude here. And let's see what that looks like in the frequency domain. So if we model, or we look at V out, I think we had about 27 dB initially. Now we get about, that's about 22 dB, so 5 dB worse distortion. So, and that's something that we would expect to be modeled fairly well. So if 3K didn't work, 4.7K works. Let's do one more experiment and then we'll finish up. If I make this 4K and run, and then let's look at our FFT. Let's see, view, I have to be in this trace here. View FFT of out. So we had 27 initially on that second harmonic. Now we have 32 dB to our second harmonic and 52 dB to our third harmonic. So we're getting better and better distortion performance, but see earlier discussion, as we start reducing this, we start encroaching on Barkhausen's criterion. So again, this is a way of letting students build circuits that don't come up and oscillate, that fail, and figure out what it takes to work in simulation, and then start reconciling that against benchtop measurements here. Okay, so back to PowerPoint, and that was my last slide here. So hopefully that gave you a sense of some ways that you might employ simulation in labs, either in conjunction with hands-on labs or on their own if you have a lab that isn't possible with the equipment that you have on hand. And with that, we will turn it back to your live presenters and moderators. Thank you.